All right, let's kick off another deep dive. Today we're looking at some really cool research
Yeah.
from Princeton and Google
Yeah.
about robots,
Okay.
learning to grasp objects. But what's really interesting is they're focusing on these really cluttered environments.
Uh-huh.
Like imagine spaces that are so packed, even we'd have trouble grabbing stuff.
Right.
And the coolest part, these robots aren't just picking things up.
Uh,
They're actually learning to push objects around to make grasping easier.
Interesting. That's a pretty different approach.
Yeah.
Most robots just try to grab things directly.
Yeah,
But this is like they're thinking ahead.
right. It's like strategic clutter clearing.
Exactly. And it's especially important when things get messy.
Okay, so picture this.
Okay.
You're trying to get a specific book off a super crammed bookshelf. It's like an obstacle course for your fingers.
Yeah, I get it.
Now, think about a robot trying to do the same thing, like in a bin full of random stuff.
Right. Even with all the advances in grasping tech, clutter is a nightmare for robots. It's like a puzzle that's always changing.
So, so how are these researchers tackling this?
Well, they're using this method. It's called deep reinforcement learning
Okay,
to train the robots.
I've heard of that. It's kind of like training a dog with treats, right?
Yeah, kind of. The robot gets these digital rewards for successful grasps.
Watch out.
But here's the really cool part. The robot's not just pushing randomly. It's actually looking at the scene
Uh-huh.
and making decisions based on individual pixels.
Wait, hold on. Individual pixels.
Yeah.
That's crazy. It's like it's thinking, if I move this pixel, I can grab that one.
You got it. It's using two special neural networks,
Okay.
one for pushing
Okay.
and one for grasping. They work together to analyze the scene, figure out the best way to go about it.
So it's not just identifying like block, cylinder.
Right?
It's seeing how it all fits together, like we would looking at a messy table.
Exactly. And they're using this really interesting type of neural network
Oh.
called a fully convolutional network, FCN for short.
Okay. An FCN. And what's special about that?
Well, FCNs are really good at understanding relationships between different objects in an image. Like, think about when you're looking at a puzzle.
Right.
You see how all the pieces fit together.
Mhm.
The FCN helps the robot see the whole picture, not just individual things.
So the FCN is like the robot's spatial awareness then.
You could say that. It helps it plan better pushes, taking into account the whole layout of the clutter.
So I got to ask, how well does this actually work? I mean,
Mhm.
are these robots actually getting better at picking stuff up in these messy situations?
Oh, yeah. The results are really impressive.
Really?
Yeah, the robots trained with this pushing and grasping strategy, they were way more successful at picking things up compared to the robots that only use grasping.
That makes sense, right? You clear a path, you're more likely to get what you want.
Right.
But are they wasting a lot of time just pushing stuff around?
That's what's surprising. The researchers measured something called action efficiency.
Okay.
Basically, it tracks how many actions the robot takes to do a task. Fewer actions, more efficient. And guess what?
What?
The robots using this pushing and grasping thing, super efficient.
Wow, so they're not just randomly shoving things, they're figuring out the right pushes.
Exactly. It's
Yeah.
really cool to watch. It's like they're tidying up their workspace,
Like we would.
Yeah, sometimes they even do multiple pushes to make a perfect path.
Amazing.
Ah.
So not only are they better at grabbing things in clutter, they're faster and more efficient.
Uh-huh.
This has got to have some real-world applications.
Oh, yeah.
Are they just doing this in simulations?
Nope, they did real-world tests, too. Really encouraging results.
Oh,
They used like 30 different objects, including some with shapes the robot had never seen before.
so they can handle new stuff? That's awesome.
Yeah, it is. But there are still some limitations. For example, objects with really weird shapes can still be tricky.
Okay, yeah. Like if the surface is super reflective.
Yeah, that can mess with the robot's depth perception. It's like trying to grab something when you can't tell how far away it is.
Makes sense. But even with those limitations, this is huge, right? Robots learning these complex strategies.
It's amazing. It's way beyond just simple pre-programmed movements.
It really makes you rethink what robots can do. So how did they train these robots to learn so quickly? I'm thinking weeks, maybe even months of trial and error.
Actually, not even close. They train them super fast. Like, in their simulations, they hit 70 to 80% success rate for grasping after just a few thousand steps.
Seriously, that's way quicker than I thought. What about in the real world?
It was pretty fast there, too. They got effective pushing and grasping going on a real robot in under 2,000 transitions.
So like how much time is that?
About 5.5 hours of actual training time.
Wow, 5.5 hours. I thought this kind of deep learning stuff took, like, forever. I remember reading about other research that needed millions of training examples.
Yeah, some of them do, but their approach here is really efficient, especially using that pixel representation we talked about.
Right, right. And you mentioned those pushing rewards they use during training
Yeah.
to encourage the robot to, change the environment.
hmm
How important were those rewards in the end?
That's a good question. It turns out they weren't totally essential. They did an experiment where they took away those rewards for pushing, so the robot only got a reward if it actually grabbed the object.
So it had to figure out on its own that pushing could help it get there.
Exactly. And get this, even without those specific pushing rewards, it still learned to push and grasp effectively.
No way.
Yeah.
So it wasn't just memorizing a set of rules.
Yep.
It was learning something deeper about how pushing and grasping work together.
You got it. It's a cool example of what we call emergent behavior in AI.
Oh, yeah, I've heard of that. It's when they do things we didn't program them to do, right?
Exactly. It comes up with its own solutions. So, want to dive a bit deeper into how those neural networks work.
Okay, yeah, let's do it. You mentioned two separate networks, one for pushing, one for grasping.
Right. Both of them are based on this architecture called DenseNet.
DenseNet. Rings a bell. Isn't that one of the best architectures for image recognition?
It is. They actually pre-trained these DenseNets on ImageNet. It's this huge data set of images, gives them a really strong foundation for understanding visual information.
So they're basically giving the robot a head start with
Exactly.
networks that already know a lot about how the world looks.
It really helps speed things up. But the trick is, how do you go from recognizing images to actually controlling a robot?
Right, because images are flat, but the robot's working in 3D space.
That's where they got really clever. They took the robot's sensory input,
Which is,
basically a 3D point cloud from a depth camera,
okay.
and they turned it into a 2D height map image.
A height map. Is that like those maps of mountains and valleys where the colors show the elevation?
Perfect analogy. They made a topographic map of the tabletop where each pixel shows the height at that point. It's like turning a complex 3D scene into something the networks can easily understand.
So they made it simpler, but in a way that those image networks already knew how to handle.
Exactly. And it worked great. By training on these height maps, the robot got a really good grasp of its environment and how to change it.
This is really cool. It's like they're finding these creative ways to connect the world of data with the physical world.
Yeah, it's not just about the algorithms. It's about bringing together different areas of research, computer vision, machine learning, robotics, to make something truly new.
I'm loving this. Any other technical tricks they use to make this work so well?
Yeah, one more key thing. They didn't just use the height map as is, they rotated it into 16 different orientations.
Really? Why would they do that? Wouldn't that make it harder to learn?
You'd think so, but it actually made it more efficient. Remember, the robot's learning to push and grasp in a specific direction. By rotating the height map, they basically showed it the same patterns from different angles.
So like teaching it to be adaptable.
Right. Instead of learning separate rules for each orientation, it can generalize its knowledge.
And that helped it learn faster, I guess.
It did. This rotation trick meant they needed less training data overall.
They really thought of everything, huh?
They did. It's a great example of how important it is to design the training data carefully.
We've covered a lot. Pushing and grasping synergy, deep reinforcement learning, those pushing rewards, the neural networks, height maps, rotations. It's amazing how it all comes together.
It really is a great example of cutting-edge robotics research.
But let's zoom out a bit. What does this mean for the real world? How could this change things?
Imagine robots that can just blend into our everyday lives, helping with all those tasks that are too dangerous or repetitive for us.
Oh, like doing the laundry. I love that.
Ha, exactly. But it goes way beyond that. Manufacturing, logistics, even healthcare could all be transformed.
Yeah. It's not hard to picture robots working with surgeons, handling those tiny instruments.
Right. Or think about them working in disaster areas or places that are dangerous for humans.
The possibilities are huge.
They are. And this is just the beginning. What we're seeing now is just a glimpse of what robots will be able to do.
Speaking of the future, what are these researchers working on next? Are they taking this even further?
They are. They're looking at other actions beyond pushing and grasping. Things like rolling objects, toppling them, even stacking them.
Wow, so giving them a whole toolkit of ways to interact with the world.
Yeah, and it makes you wonder, what are the limits of what they can learn?
It's an exciting question.
It is. And as they get better at manipulating their environment, Who knows what they'll be able to do?
This is seriously mind-blowing.
Okay.
So we've got robots that can clear a path to grab what they need. They're fast, efficient, and can even handle new stuff.
Mhm.
What's the main takeaway here?
I'd say it's that robots aren't just limited to simple pick-and-place tasks anymore. They're starting to understand the physical world in a much deeper way.
It's like they're going from basic grabbing to like mastering object manipulation.
Exactly. And that could change a lot of things. But it also brings up another interesting question. If they can already rearrange their environment to grasp better, what else could they do if they had an even better understanding of the world?
Hmm, that's something to think about. Where do you see this research going the next few years?
I'm really interested in seeing how this works for more complex tasks and environments, like robots that can not only grasp and push, but also assemble things, pack boxes, maybe even help with surgery, all while working safely alongside us.
Wow, that's a future I want to see. Sounds like we're entering a whole new era of robotics, where they're not just tools, but collaborators.
It really does.
Thanks for taking us on this deep dive. This was awesome.
My pleasure. I always love talking about this stuff.
And for our listeners, if you want to check out this research, we'll link to the project page in the show notes. You can see some videos of the robot in action. It's really cool. And if you want to learn more about deep reinforcement learning and all this, we'll have some resources for you there too. So, until next time, keep those brains buzzing.
They are. They're looking at other actions, beyond pushing and grasping.
Oh, like what?
Things like rolling objects,
Okay.
toppling them over, maybe even stacking them.
Wow. It's like giving them this whole toolkit of ways to mess with the world. Makes you wonder, what can't they learn?
It's a good question. And as they get better at this stuff,
Yeah.
manipulating things,
Yeah.
who knows what they'll be able to do?
This is mind-blowing. Okay, so we've got these robots that can clear a path, grab stuff, they're fast, efficient, can handle new things. What's the big takeaway for our listeners?
I think the main thing is robots aren't just stuck with those simple pick-and-place tasks anymore.
Right.
They're starting to understand how the physical world works in a much deeper way.
Yeah, it's like they're graduating from grabbing to like really mastering how to move things around.
Exactly. And that has huge implications, right?
Yep.
But it also raises another question. If they can already rearrange stuff to grab better, what if they had an even deeper understanding?
Yeah, what else could they do?
Right.
What else?
That's a great question. So where do you see this going in the next few years?
I'm really excited about how this applies to like more complex tasks and environments.
Okay.
Imagine robots that can, not just grasp and push,
Yeah.
but also assemble products, pack boxes, maybe even help with surgery, all while working with us safely.
Wow, that's incredible. That's a future I definitely want to be a part of. Sounds like we're moving into this whole new era for robotics, where they're not just tools anymore, but actual collaborators.
It really feels that way.
This was a fantastic deep dive. Thanks for joining us.
My pleasure. Always happy to talk about this stuff. And for our listeners, if you want to dig deeper, we'll link to the project page in the show notes. They've got some really cool videos of the robot in action. Plus, if you're interested in this whole world of deep reinforcement learning, we'll have some resources for you there too. So until next time, keep those brains buzzing.